Hi everybody, thank you for joining Synthetic Intelligence Forum Online. My name is Vic and I'm very happy to welcome you to today's session on demystifying quantum machine learning. Very happy to have a friend, Luis Serrano, on our stream today. Luis doesn't need an introduction. He is already a very well-known public intellectual and famous science communicator when it comes to topics around machine learning, deep learning, and now increasingly reinforcement learning on the internet. Luis has authored an excellent book, Grokking Machine Learning, that is really going to be quite helpful to folks from a practical as well as a conceptual perspective. Also, Luis has a very nice website and as well as a YouTube channel where he explains the concepts related to machine learning, deep learning, and reinforcement learning in very straightforward and simple terms. Luis has created some excellent content for Udacity on AI. I'm sure many folks actually know of Luis through that. So very happy to have Luis come and talk today to us about demystifying quantum machine learning with a focus on quantum generative models. So without further ado, it's my pleasure to welcome Luis to the stream. Luis, I'll add your slides to the screen and please take it away. Welcome.
Thank you very much, Vic. Thanks for the kind introduction. It's an honor to be here at this great seminar. So thanks for the invitation. I want to thank everybody for attending today. So let me present my screen. And yes, so today I will talk about demystifying machine learning. And again, I'm a quantum artificial intelligence research scientist at Zapata Computing in Toronto. And I like to make this a conversation. So I have the chat right in front of me. So please ask me any questions. Feel free to make any remarks, anything you find interesting, and I'll be sort of going back and forth. And if we go into a discussion about something tangential, then that's great for all of us. So yes, feel free. All right. So just without further ado, quantum computing and quantum artificial intelligence has been more and more popular this year. So in the same way that all roads lead to Rome, all industries are finding that they have applications that can be enhanced by quantum computing, by quantum machine learning, and that's just going to grow more and more as quantum computers get more and more qubits. So I'll tell you a little bit about computing. What we do is we have a platform for quantum computing, and that platform is useful for businesses to run their workflows either on classical or simulations or actual real quantum computers, and also for research groups, government universities, etc. So I'll have some links later if you're interested. I'll tell a bit about what we'll see today. So I'm going to tell you a bit about quantum computing, and Vic has told me that this is a very educated crowd that knows a lot. I will still give you a tiny introduction just to get in tune with the notation I use, etc. I'll tell you a little bit about generative machine learning, which is the field that we're going to tackle with quantum computing, and where they combine into quantum generative machine learning. This I won't talk about, but I'll give you links to a nice coding lab in PyQuil where you can do all the stuff we do today on your own time. It's on GitHub. And there's also a demo of the platform that we have at Zapata, which is Orchestra, where you can actually use a quantum computer. So I'll give you a link for that. So first, let's talk about machine learning very quickly. So what is machine learning? So the most popular field of machine learning right now is supervised machine learning, which is basically answering questions, right? So we have our model, and our model is given a data set, and this data set has labels. So for example, here's an image data set with labels dogs and cats, and the goal of the model is that it learns the data set, and when you give it something without a label, it guesses the label. So it goes, okay, this image is probably a dog given the data you gave me. That's sort of the simplest form of machine learning. Then there's unsupervised, which is a little more sort of high level, in which the data doesn't have labels. It doesn't say dog, cat, automobile, and so the computer can't guess them, but instead it can do things like maybe group them apart and say, okay, well, I have no idea what you gave me, but these things over here are similar to each other, and these things over here are similar to each other, etc. And a very special branch of unsupervised learning that's got a lot of attention lately for the things it does is generative machine learning, which it does kind of the opposite as answering your question. It instead of saying this image corresponds to a dog, it does the opposite. You tell a dog, and it goes, here it is. I drew one. So it generates new things. It can generate music, poetry, solutions to problems. It can generate. The coolest part is that it generates like things like images, faces, videos, and you must have seen deep fakes and all these things. Why are we? This is the one that we're going to tackle, and I'll tell you in a minute why is it that we're going for that one. But let me tell you a bit about, in a very high level, how classical and quantum machine learning work in the generative sense. So a classical machine learning model and a quantum generative model. The classical machine learning model, you have something like a neural network or something with input and output, and you throw in random numbers and numbers come out, and the goal is to make what comes out look like what you want it to come out. So you compare it to the data set, to the images, and you update the parameters. So you have things like, you basically have numbers coming in and numbers coming out, and there's addition, multiplication, activation functions, and you want to make the parameters what you want them, so the data comes out as you want it. And with quantum machine learning, it's the same thing, except instead of numbers, you have qubits. So these qubits, they operate on each other, and then you get some output. And again, you compare this output with what you want it to be, and update the parameters. I'll tell you more about what these parameters mean. But basically, what you have in classical computers with numbers, which is operations, with qubits, it becomes things like rotation, entanglement, gates, etc., which I will tell you a bit. But a question: why do we care about why do we tackle generative models with quantum computers? Should it make more sense if we go straight for the easy stuff like supervised learning, etc.? And there's many reasons for actually caring more about generative models. Well, one is that supervised learning has been done very well in classical computers. If I were to find a quantum algorithm that speeds up linear regression, that's wonderful, but it'd be hard to notice, right? Because it's already very fast. Another reason that is a bit more meta is that classical computers are good for input-output, right? For you put in a number, you get a number out. Quantum computers are more are better for generating random things out of nowhere, right? A classical computer can have a hard time generating random numbers. As a matter of fact, they can't. It has to be pseudo-random. Everything a classical computer says is scripted from a formula, whereas a quantum computer can actually generate random things. So as long as you teach it the right distribution, it will generate things for you. And that's why we tackle generative models. Also, in a classical computer, sampling is pretty hard. Like sampling, you have to sort of fake random input to get random output, and that can be a problem. So that's one reason why we're going for generative models. So I'll give you a laundry list of some generative models. In classical computers, you have generative adversarial networks that are very popular, restricted Boltzmann machines, variational autoencoders, and each one has its own quantum sort of counterpart. We have quantum generative adversarial networks, quantum Boltzmann machines, quantum circuit board machines, etc. And the example that I'll show you today is an example of a quantum circuit board machine. So it's a QCBM. In short, is something that if you give it a lot of data, it tries to learn the distribution of where that data came from. Okay. So if there's any questions, feel free to ask them in the chat, and I'll be taking a look. I'll start with a quick introduction to quantum computing. So what are qubits, or at least how I look at them? So when I see a classical computer, I think of a bunch of switches, right? A bunch of on and off switches. You have a 0 and you have a 1. And for the purpose of this talk, 0 is always red, it's always up, and 1 is always blue, and it's always down. A quantum computer has a lot of states in between, right? A qubit has a lot of states in between. So it resembles more of one of those switches that you can slide in up and down or in the middle. And the state is called, the 0 state is up, the 1 state is down, but you can have a superposition of the two. You can have half-half, and you can have like more of one than the other one. And you pretty much have this whole spectrum. You can slide it to wherever you want. But there's actually more than that. It's not just a spectrum. It's actually an entire sphere. So imagine if the switches in your house we're all spheres, and any direction that it points, that you can pick a, in classical computer you can point up or down, but here you can point in any direction that your fingers can point. That's a different qubit. And so basically any point in this sphere represents a different qubit. And the higher you are, the more zero you are, and the lower you are, the more one you are. And everything in the equator is a half superposition, and it's a different one. Okay. I like to see them like this. It's kind of like a vector where you show how much percentage of up you have and how much percentage of down you have, and you have positive numbers on one side and negative numbers on the other. In reality, it's just square roots for mathematical and physical reasons. If you like to look at the square roots, fantastic. If you know, you can do like me and put on your green goggles and not see the square roots and pretend they're not there, but they have to be there for the math. And so, quick quiz. There's a little lag in the chat, so quick quiz. What do you think it's this qubit here? If the one on the right is √5, and the one on the left is √5, -√5, what do you think is the one on that's pointing the closest to us? What do you think are the two numbers there for how much up and how much down you have? Let's see. Give people a second to give it a try. Yeah, Michael says we can think of this as matrices too. Yeah, we can think of it as matrices and vectors. So I'll tell you the answer. √5 and 0 says Rava2. Yeah. So actually, since one is the positive √5 and the other one is negative √5, what you have in the middle is the imaginary number. So you have square root of -5 minus 0.5, or I times the square root of 0.5. So basically everything in this is a pair of complex numbers. And where is this complex number? 1000 root of 0.5. Yep, this is correct. We have complex numbers. So think of any. I like to avoid the complex numbers when I'm talking about qubits, but you can always think of them as they are there. But basically every point in your sphere is a pair of complex numbers. And I write them as a vector, but sometimes it can be written as a wave function, like this much of 0 plus this much of 1. You can do whichever you prefer. I like to do vectors because then I can multiply by matrices whenever I want. But in general, for the qubit is a complex number times 0 plus another complex number times 1, where the norms of these complex numbers squares add to 1. And for a very, very nice technical reason about phase transitions, you can always think of the first one as a real non-negative, and the second one can be complex. But again, I will always sort of think of them as real and during this talk. But feel free to think of them in the back of your mind as complex. So the notation we'll use today, we can think of qubits as a point in the block spheres, an arrow, as a vector, or as a wave function. So something like this. And I will always toggle between these ones, but the one most consistent thing is the blue and the red. So feel free to, again, feel free to stop me if any clarification is needed. Some qubits are special. So we have the North Pole, which is the 0, the South Pole, which is the 1, and the two superposition states, which are √5, and √5 minus √5, which are called plus and minus. So how about this? I mean, we have a bit is a 1 or a 0. That's a 1 bit of information. A qubit holds an entire complex numbers. You can fit all the information of the human race into a complex number. It's infinitely many decimals. So what's the catch, right? I can't store infinitely many information here. And the catch is measurement. So when you observe a qubit, you lose all that information because, let's say, when I observe this qubit, two scenarios may happen. Let's say this qubit is √0.7 up and √0.3 down. And two things can happen. Either the qubit becomes a full 1, a full 0, or a full 1. And you never knew where it came. And the probabilities are given by the squares of the two coefficients. So with 0.7 probability is going to go up, 0.3 probability is going to go down. And we're going to have these we're going to have these circuits pretty often today, which is you have the qubit, and it goes here, and it's almost like two magnets pull it, and one of them wins. And let's say this one wins, and you end up with this. And if you run this experiment many times, you're going to see that around 70% of the time, you're going to end up with an up, and 30% you're going to end up with a down. So, all right, let's go to quantum gates. So in classical computer, we have gates, right? Because we have we can flip the switch on and off. That's the NOT gate. In quantum computers, we also have gates, and you can think of them as pretty much any transformation on the sphere, any rotation or anything like that switches up to down and down to up. Since a sphere has 3 dimensions, I can rotate it like this, like through the x, y, or z axis. And so the rotation through the x-axis is called Rx of theta, given the angle. The rotation through the y-axis is called Ry of theta, and we specify the angle again. And the rotation through the z-axis is Rz of theta. So these are my gates. And if you like matrices, here are the matrices corresponding to the gates. If I were to multiply this matrix by the vector of the qubit, what I obtain is the rotated vector. So they are there for doing mathematics. I like to imagine them in my head as rotating a sphere, but this is the math. And if you pick the correct angle, you may get the matrix like this one, for example, and I multiply it by a vector to obtain another vector. So you're always doing matrix algebra. There's also the Hadamard gate, which is, as I said, the one that toggles between the 4 most popular states. And this one can also be expressed as a matrix that sends the up state to the perfect superposition, and it's given by this. So when I multiply by this, I get this vector. So think of Hadamard gate as the one that turns the up vector into the perfect superposition. So as I mentioned before, the quantum computers are fantastic for generating random numbers, and the easiest random number generator is simulating a coin toss. So how do we simulate a coin toss? Well, I pass it through, for example, a Y gate, this one, with pi. Oops, I'm not sure if I meant pi or pi over 2. But anyway, the one that rotates at these many angles. And that one now has a 50% chance to go up and 50% chance to go down. So when I observe it, it either goes up or goes down, and boom, I got my coin toss. If I run this many times, I'm roughly gonna get 50% of up and 50% of down. So what would I do if I wanted to tamper with this coin? If I want to do a biased coin toss? Well, what I do is I mess with this angle. So if I were to use this angle, 2 arc cos of 0.7, then this rotates it this much to have it 70% of the way up. And when I flip the coin, it has more chance of going up than down. So I have tampered with my coin as much as I want so that I get 70% of the time heads and 30% tails. All right, so now let's talk about when the really weird quantum stuff happens is when particles start acting with each other. There's something called entanglement, which I find absolutely fascinating. Which is, I like to imagine in the following way. Let's say we have 2 people, and they have a 50% chance of being happy and a 50% chance of being sad. So if these 2 people have never met and don't know each other and don't influence each other, what are the probabilities that they're both happy? Well, it's going to be 50 times 50, which is 25%. And each combination of the 2, happy, sad, sad, happy, sad, sad, is 25% because they don't know each other, right? They're unentangled. But imagine if, let's say, they're happily married. So if I were to ask one of them, are you happy? Then I know that the other one is happy too, because they are just completely entangled. If one is sad and the other one is sad. So these 2 things in the middle never happen. And all of a sudden, the probabilities change from 25, 25, 25, 25 to 50, 0, 0, 50. That means that these people are entangled. The same thing happens with particles, right? Imagine if I have my 2 particles in perfect superposition. So the probabilities of them being up or down when I observe them are 50-50. So the probability of getting each one of the two combinations, up, 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 down, down, up, down, down, is 25%. But imagine now that if I observe one of them and it's up, then when I observe the other one, is going to be up for sure. That means they are entangled. Okay. And so therefore, in the same way, up comes with probability 50%, down comes with probability 50%, and the other two never happen, right? So the product that you see in the right changes from 25, 25, 25, 25 to 50, 0, 0, 50. That means these particles are entangled, and that's actually called the Bell state. It's sort of the most entangled the two particles can get. They don't have to be fully entangled to be entangled. So let's do a small, help me out with numbers here. If I have one person that is happy 70% of the time and sad 30%, and the other one is happy 60% and sad 40%, and they don't know each other, how often are they, what is the probability that they're both happy, right? Who can help me out with these numbers? So I'll wait for, well, maybe I'll say it since there's a small lag. The probability is the product, right? So it's 0.7 times 0.6, which is 42%. The probability that we have happy sad is 28%, and so on. 18% and 12%. So in the same way, if I have two qubits that are not entangled and their wave functions are these, then the tensor product is the product of these two, or the probabilities of the square roots of the probabilities of being up, 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 down, down, up, and down, down. So I'm going to refer to it as tensor product pretty often. When I have two qubits, I will refer to as the joint probabilities as well, and that's going to be the joint wave equation. This could perhaps not be so easy to split, right? Like you see how the first equation, I went from the probabilities to the tensor product, but if I were to change these numbers at the right, I may not be able to write it as the product of two qubits, right? Because I'm not going to find two numbers that when I multiply them, I get the thing at the right. The way to tell is if the product of the first and the fourth is equal to the product of the two middle ones. If I have that, then they're not entangled. But if I don't have that, they are entangled. So if I cannot write the joint wave equation as a product of the wave equations of the two, then they are entangled. Any questions? Feel free to stop me. So now that since we have single gates, we also have entangling gates. So the entangling gates they're meant to mimic what the classical gates do. So we have the classical gates, we have the AND gate and the OR gate. And the AND gate, as you know it gives you a 1 if both of the inputs are 1, and the OR gate gives you 1 if either one of the inputs is 1. With quantum gates, you have to have as many inputs and outputs. So you're not going to be able to have two inputs and one output. Everything has to preserve. And so we have the C0 gate. And what the C0 gate does is it's sort of, it's called a controlled knot. And what it does is that if the first one is up, then you don't do anything. And if the first one is down, then you flip the second one. So in other words, it does this. Once you have the joint wave equation, then it just flips the last two. And if you like to see things as matrices, this is the matrix corresponding to the control knot. And it does the following to the wave equation, to the wave function. So now let's look at the two Bell states, right? The two Bell states are the ones that are either up, up, or down, down, or either up, down, or down, up. And I'm going to abbreviate them as this because I don't want to be writing two to the end things every time. So now let me show you how to entangle qubits. Okay, here's an exercise. The question is, how do you start from up, up, and combine some of the gates that I've shown you so far to get the Bell state? Okay, so in other words, how do I go from the qubit to the left to the qubit to the right? Then when I start sampling, I get roughly 50% of the time I get up, up, roughly 50% of the time I get down, down, and roughly 0 times I get any of the other two. So here's how to do it. You mix a Hadamard with a C0. So what happens with the Hadamard? These are my wave functions. The Hadamard rotates it 90 degrees, the top one. So I rotate it 90 degrees. And now I have the following two qubits. The first one is in perfect superposition, and the second one is still up, right? And I can express this as the joint wave function, right? And now I go to the C0 gate, and the C0 gate does something weird and entangles them. And the reason is because the C0 gate will apply this transformation. And now I have my entangled state. So that was a little bit more challenging than finding the superposition of one qubit to entangle two qubits, but it's doable. And this is doable in quantum hardware. So we went from here to here. There's an easier way. There are some gates that are entangling gates. And I like this one, kind of have to see it in matrix form. But the matrix is this. And if you pick the right angle, it'll entangle the two gates. So it's just kind of a 2-qubit version of a single X, Y, or Z gate. And I'm just showing you the Y, but there's one for X, there's one for Y, and there's one for Z. So that's pretty much all for the introduction to quantum computer. Now I'm gonna tell you how this ties in with machine learning, and it's an interesting way, but it's because it kind of goes in both ways. You kind of use machine learning to help with quantum computers, but you kind of what we're doing is we're using machine learning concepts to create circuits. So let me show you what a quantum circuit-born machine is. So let's go all the way to 4 qubits. And with 4 qubits, you can have each qubit, again, is up and down. So you have 16 possibilities, all of them up, all the way to all of them down, all the combinations, right? And the wave function can be basically assigned any numbers to these 16 possibilities where the squares add to 1. And so to save space, I'm just going to put the non-zero ones. What does this mean? This means a wave function in which half of the time, roughly, I'm going to get 4 ups. 10%, I'm going to get 2 ups, 2 downs, and so on. All the way to 10% of the time, I'm going to get 4 downs. Okay? And so let's summarize a little bit. At the very beginning, we created a superposition state, which is the one that sends an up to a superposition between up and down. So this is flipping a coin. And that was easy, just a Hadamard gate. Now, I create a slightly hard one, which is the Bell state, right? Which is 2 coins that if I flip them, I always get either 2 heads or 2 tails. So that was the circuit that I showed you recently, right? A Hadamard plus a C0 gate. Now it gets a little harder. Let's say I want to do 3 coins that when I flip them, I always get either 3 heads or 3 tails. I never get anything else. This is a harder circuit to build, but it's doable. And a much harder one is with 4 coins, right? So these are the perfect superposition states. And the question is, can we build a circuit? Can we attach Hadamards and C0s and Ys and X and YYs and everything so that we prepare this state, this perfect superposition state in between n qubits? And so this is much harder, and it's hard to do it by eyeballing it. And that's where we use the QCVM. So I'm going to show you how to sort of use machine learning to build these circuits. Okay. So the idea is the following. The idea is very simple. It's what we did with the single coin flipping, right? If I wanted to create, for example, this state, which is 1 over root 2, 1 over root 2, the perfect superposition state, well, if I use a random angle theta, I get some numbers A and B. All I have to do is I have to play with the angle, right? I have to play with the angle to get the superposition that I want. And that's sort of machine learning-ish, right? Because I'm starting with my answer and twisting my parameters to give me the answer I want. So for 2 is the same thing. I'm going to have a YY gate, okay? And I want to start with a 0, 0 and end with this perfect superposition of 0, 0 and 1, 1. Well, all I have to do is I have to play with this angle until it gives me what I want. Right? Again, machine learning style of a procedure. And with 3 gates, it's the same thing. I'm just going to complicate my architecture. I'm going to say, okay, my circuit's going to look like a YY between the first 2 qubits, a YY between the first and the third qubit, and a YY between the second and the third qubit. And I want to start with a 0, 0, 0, and I want to end with the perfect superposition of 0, 0, 0, and 1, 1, 1. And all I want to do is play with my 3 angles. So I'm going to twist them around, increase this one a little bit, decrease this one a little bit, until I get what I want. Pure machine learning concepts, right? And for 4 qubits, I can keep doing this, right? So in the same way that we do neural networks, that we sort of decide on architecture and then try to find the parameters somehow through gradient descent or through something, we have some set architectures. And so the most 3 popular architectures in QCBMs are the star topology, which is connect the first qubit with everything. The line topology, which is first and second and third, third and fourth, etc. And the all topology, which is throw in all the possible combinations between 2 qubits. And we're going to play with these parameters until we get the perfect parameters for what we want. Maybe a good time if you wanna ask me any questions about this. Feel free to ask them in the chat. Let's see. This is the paper that I'm gonna tell you about. It's Benedetti, Perdomo, and a few other people, where they introduced the quantum circuit-born machine. So this is kind of how it looks. Basically, I like to think of it as you start with 4 qubits in the up state, which is the sort of the beginner state. And then with some angles, you rotate them in the y-axis. Then with some angles, you rotate them in the z-axis. And then you start entangling. So you entangle the first 2 based on some angle. You entangle the first and the third based on some other angle. Then you entangle the first and the fourth based on some other angle. And then you observe. And then when you observe them, remember, they either go up or down. And you started with up, 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 and ended with up, down, down, up. So I'm going to record that. Okay, that was one run of my circuit for some angles, theta 1 up to theta 11, right? And what I'm going to do is, let's say that I want to build a circuit that gives me this wave function. Now, I cannot observe the wave function, but I can sample many times. So if I want, for example, these proportions, then what I do is I run my circuit, and let's say I got down, up, down, up. So I record that. Then I run my circuit again, and let's say I got up, down, up, up. So I record that one. And I do this many times, and I get some histogram. Whoops, sorry about that. My computer's a little slow. So if I run this circuit many times, I end up with some histogram. And now I'm going to chase the histogram that I want. Okay, so let's say that I want to create the perfect superposition between 0, 0, 0, 0 and 1, 1, 1, 1. So what I do is I run this many times and see what I get. Yeah, my computer's like lagging a little bit, and it's just... Okay, so the training process is the following. I start with up, 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 and I see what that gives me after sampling many times. Now, what I really want is the one that gives me 50% of the time at 0, 0, 0, 0, and 50% of the time at 1, 1, 1, 1. So I compare these two using some comparison. I'll tell you later about what comparison. And then I remember that my circuit had a bunch of angles, and I use this comparison to update the angles a little bit so that it gives me something closer to what I want. Okay? And I run this process many times. I compare. I update the angles. And I get a little better until one day I got something pretty close. And that's it. That's the training process. Okay? So for example, I can go from a circuit that gives me this random distribution to a circuit that gives me the distribution that I wanted. Are there any questions on this process? I will be more specific. Vic, how am I doing with time?
All good, Luis. You're doing pretty good.
Okay.
Yep. Keep going. All
okay.
Good.
You let me know if I'm close to. So here's a little example before we get into into how the training actually happens. There's this coding example that you can take a look, and maybe I'll share it with you in the chat later. But feel free to go to Zapata Computing and GitHub. It's called tutorial ODSE QML, and it's got the coin toss, the entanglement generator, and the quantum circuit board machine for this simple data set. It's a toy data set where you have the bars and stripes. So pick your favorite rectangle, and all the either combinations of bars or combinations of stripes. So you can also have the whole rectangle or none of it. That's all the stripes or no stripes. So here's the example, and here's how you would turn it into qubits. I'm just going to turn this into 0, 0, 1, 0, 0, 1, 0, 0, 1. I'm just going to read them like this. And so I can turn every single one of my elements in my data set into a bunch of qubits. So here is, for example, 0, 0, 0. This is for 2 by 2. I have all my data set turned into qubits, and I'm only going to look at bars and stripes. So it's this 6 among the 16. And so my bars and stripe distribution is this one, right? I have a 1/6 probability to obtain each one of the bars and stripes, and 0 for the rest. So this is my wave function on the right, which I'm going to write, abbreviate to this. And basically what I want is, I want to start with a QCBM. I want to start with a random distribution and train a QCBM to prepare the right state to give me the distribution that I want. So the training process is the following. I want to get from the one on the left to the one in the right. And so I'm going to first show you the loss function. So I'm comparing the distribution that I'm obtaining with the one that I really want to obtain. And the way to compare them is using several loss functions. One is called KL divergence. There's also log likelihood, maximum mean discrepancy, etc. I'm going to show you KL divergence. So I'm going to show you a way to compare two distributions in a way that if I plug in the two distributions in a function, it gives me a high number if they're different and a low number if they're very similar. It's basically the equivalent of a loss function. And KL divergence is very simple. If I have, for example, this distribution P and this distribution Q, I want a number that is small because they're similar. And if I have this P and this Q, I want a number that's big because these two are very different. And the formula is simple. It's just summation of P of X logarithm of P of X over Q of X. And this is just gives us a big number if there's different, and a small number that if there's a small number they're similar, and a big number if they're different. So that's what we're going to use. And now let me show you how to minimize the function, because just like in machine learning, if you manage to minimize the KL divergence, then you've got a good circuit, right? So there are several different methods. There's gradient descent and also other methods like CMAS or particle swarm optimization. Let me first show you particle swarm optimization. So I'm going to show you how to minimize a function, in particular the KL divergence. So basically, when you think of neural networks, you can think of gradient descent, right? So gradient descent is take the derivative and walk in the direction of the derivative and get a smaller value for your function. There's also gradient-free methods where we use other things like probability distributions to minimize our functions. And we can do gradient with quantum, because when you take derivatives of cosines, you get sines. And we can work out derivatives and use gradient base, and they've used. But the one I'm going to show you doesn't have gradients, and it's CMAS. And imagine this. imagine that you want to minimize this function. So you want to find this point over here, and you cannot take derivatives. So what I'm going to do is I'm going to hire a bunch of friends, and we're all going to search the space together in a way that will have a high probability of getting to the low point. So let's look at it from the top. Okay, so from the top, I have my space where the dark points are the low points and the light points are the high points. And I want to get to that. I want to get here, basically. I want to minimize this function. So how do I do it? Well, I'm going to get all my friends to look around, okay? And let's say that we've walked around for a bit. And I'm going to show you 3 strategies to find the minimum. The 3 strategies are pretty bad, but combined, they're pretty good. The first strategy is called inertia. The second strategy is called personal best. And the third strategy is called team best. So the best strategy is combining them all. What is the first strategy? So let's say that you have all walked around the space and you're going all in a certain direction. So inertia says, continue walking in that direction, all of you, until you're out of the space. And what is the best point that you achieved? Well, let's say it was this one. So it's not a genius strategy. The second strategy is personal best. So we've all walked around the space, and we all remember where is the lowest point that each one of us achieved. So let's say that for the first point is this one, and for each point has its own personal best they've achieved so far. So strategy 2 says, walk in the direction of your personal best. So everybody walks in the direction of their personal best. And see what's the best point you achieved as a group. So that's an okay strategy, but it's not that good, right? And the third strategy is team best. So we talk to each other, and we communicate, and we say, where among what we've all explored, which one did best? And it turns out that somebody reached this point at some point, and that's the lowest somebody has walked. So then we all walk in that direction. And let's see how well we did. So this is the best we did. So these 3 strategies, none of them works very well, but if you combine them, they work really well. So let's take 1 step in the direction of inertia, 1 step in the direction of our personal best, and 1 step in the direction of the team best. So this is adding 3 vectors, right? I take 1 step in each of the directions. And now imagine that at every step, we all do this and communicate to each other. So we keep updating our team best and our personal best. And it's easy to imagine that if we all do this, then we're sort of, as a group, reaching a best, right? And so this is a very, very good method for achieving, for minimizing a function. Any questions? Feel free to stop me. Since I have a little bit of time, then I will also tell you about another one. It's called CMAS. It's a genetic algorithm, an evolutionary algorithm. So it does the following. Let's say that, again, I want to find the minimum of this function. So I have, let's say, a population of 5 points. And what they're going to do is they're going to survive with higher probability if they are stronger. And by stronger, I mean if they have reached lower points in this function. So I'm going to use a Gaussian. And a Gaussian is, you can imagine, just as a sheet that I've raised at some point, like a bump. And I'm going to look at it from the top like this. So this is what I have in the bottom, is how I like to imagine a Gaussian seen from the top. So I'm going to use the Gaussian to help the points survive and reproduce. So what we're going to do is, first, the strongest points survive. So my 3 strongest points here are going to survive. So these are the 3 with the lowest value in the function. And now they're going to reproduce. So how do they reproduce? I fit a Gaussian through these. Then they die. And then 5 new are born based on this Gaussian. So I sample 5 points on the Gaussian. And I continue doing this, right? The top 3 survive. I fit a Gaussian to the remaining. Then they die. Then I sample 5 new points, so the next generation. And then the top 3 survive, and I continue doing this. And you can imagine that this is a good way to minimize a function, right? Because I'm always getting stronger and stronger points until maybe one day, with a bit of luck, I reach the minimum of this function. So that is CMAS. So as a conclusion, the training process of the QCBM is basically this. I start with a random parameterized quantum circuit. I evaluate the cost function to see how far is it from what I want, and I update using an optimizer like particle swarm optimization or CMAS. And I do this many times, and I end up with a distribution that close to what I want. And so that's how we build them. If you look at the lab, this has been worked out, and the winning angles are these. The winning angles for the full topology are these. So that's pretty much all I have to say on QCBMs. Let me tell you a bit about applications, and Vic, feel free to stop me if I'm close to the end. But applications can be anywhere, right? Because generative learning has application on image generation, video generation, etc., portfolio optimization, etc. So I'm gonna show you two: image generation and portfolio optimization. So image generation is a very, very popular field. These people don't exist. They have been generated images using a GAN. And so GANs are very, very special. So I'm going to show you a bit. Obviously, a GAN is, obviously a quantum computer is not big enough to fit a face. So what we're going to do is something a little smaller, but that shows success. And it's this paper of Rudolph and other co-authors. And what this does is it enhances a generative adversarial network with a small QCBM. So let me tell you a bit about what a generative adversarial network is. So in a generative adversarial network, you have a generator and you have a discriminator, okay? And what the generator does is the following. It picks a point from some small space randomly. It sends it to the generator, and the generator generates noise. Because what you're trying to do is, one of them is a art forger and the other one is an art critic. And so the art forger is trying to create better and better images, and the art critic is trying to tell them apart from the real from the fake. And as you train them both, they both get better. So the generator gets better at generating better images, and the discriminator gets better at telling them apart. And so we train the discriminator to say, give me this image is noise when it comes from the generator. And we train it to say that this image is an actual image when it comes from the data. So if we train those two, you end up making beautiful images. That's how you make the faces, and that's how you make digits, etc. But now here is an enhancement of this. So here's a problem that GANs have. Let's say that I pick something random out of the purple latent space, the prior, and I get some noise, and I get, if I pick a better point, I get a nice image. Because it happens that the latent space, it's naive to think of it as a uniform distribution, right? Naive to say I can pick randomly out of the latent space. There are places in the latent space where images come out, and there are places in the latent space where noise comes out. And we never care about training that one. So what this associative adversarial network does is it fakes a latent space from the discriminator. Okay, so it takes one of the last layers of the discriminator and says, when I throw in my data, where does that go in that space? And let's say it goes here. Then it uses a quantum generative model to learn that distribution, and then it sends that back to the latent space and samples out of there. And we've seen that when you sample out of there is much better than when you sample uniformly from the latent space. So there has been improvements in the type of images that get generated and the diversity of the images that get generated. That's in that paper that I show you. And the last application I want to show you is in portfolio optimization. Believe it or not, you can use this to generate solutions to things. And I'm not going to elaborate very much, but feel free to ask me if there's any doubts. But basically, you can imagine this. Imagine that with a classical method, you find the point is to find the best portfolio, right? So the best combination of stocks that will give you the best gain with as little risk as possible. And I can find some solutions using a classical optimizer. Well, I can generate some using a quantum generator, right? I just tell the computer, in the same way that you learned a bunch of images and you spit images out, learn a bunch of solutions and spit some solutions out. And believe it or not, that works. So that has been done to improve portfolio optimization. And finally, I want to point you to some to how to use this. So here's I'm going to point you to a demo that we have of Orchestra, where this is done, the QCBM example. You can look at this video, or you can also point your phone at the at this QR code, and I'll give you the link. I'll share all these links with Vic later. But the idea is that you can this demo, you can use a quantum computer to train a QCBM to generate the bars and stripes distribution. So yeah, next steps, if you're interested, feel free to check out this page, orchestra.io docs, and that is the one that has the Orchestra demo. And I think that's all I have. So let me give you some links if you want to follow me. There's this book, Rocking Machine Learning, that Vic mentioned at the beginning, that if you'd like to, I'll like to give you a 40% discount code. It's Serrano PC, and here's a link to obtain it. This is my YouTube channel where I have videos on machine learning, and some of them in quantum machine learning. This is my Twitter, Luis Likes Math, and this is a page where all the information can be found, serrano.academy. And with that, I conclude, and I'm happy to answer any questions. I see a bunch of questions in the chat, so.
Luis, thank you for the talk. And by the way, that 40% is a very special, unexpected surprise gift. That's great. So since you ended with Orchestra, why don't I try my skills at random sampling and pick some questions? We won't have time to go through all of them, but there is a question here from one of our colleagues on, can you touch a bit on the hardware and software required to do quantum machine learning in practice?
On the yeah, of course. Can you touch good question, Chantal. Yeah, the hardware and software. I mean, right now things are small, but there's a few quantum computers. There's Honeywell, IBM, Google, Rigetti, etc. The way you use it's hard to use them. So Orchestra is a way to send workflows there. Most of what I do actually is simulation. So there's a bunch of simulators that you can use. I recommend, if you're going to get started, go for Qiskit, PyQuil, Penny Lane. These get you to sort of simulate a quantum computer and play with circuits. That would be what I recommend. Yeah, I'm not sure if that was the question, or if you would like.
No, I think that's a great starting point. Thank you for that, Luis. Here's a question from Michael about, do you have any preferences about platforms or languages that, and especially if somebody wants to get started, is there one that's easier than others to pick up in your knowledge?
I think Qiskit's pretty good. Penny Lane's pretty good too. It's almost like choosing packages for classical machine learning, but I think those two are pretty good. Pennylane has some really good tutorials. So pennylane.ai I recommend. So they have tutorials on most of the basic stuff. So you get to use their they can be used like notebooks, like Jupyter notebooks.
So this one, I think, also kind of touches on the practical aspects, Luis. So I know you touched on a number of different quantum circuit configurations. When some of these systems you talked about, the software to interface with the hardware, do they give you some of these circuits out of the box that you can then sort of adapt to your specific requirements? Or do you have to build them ground up on some of these systems platforms you've mentioned today?
That's a great question. I'm not as expert in the hardware stuff, but yeah, I mean, some of these circuits are easy to build and some are not. I'll give you an example. So some architectures, you can connect quantum 1 and quantum 2 easily, but not quantum 1 and qubit 1 and qubit 2, or qubit 1 and qubit 5 is harder, right? Like sometimes it depends on the architecture. Depends on what you're doing. I tend to focus on the on the algorithm part and take the hardware stuff for granted. But yeah, there are different things you can run in different hardwares, or that are easier or harder. Yeah, but I don't know that much about it.
Okay, here's a question from Jorge. So the question is, so you talked about some of the advantages of quantum machine learning, Luis, kind of at a high level in terms of compared to traditional or classical machine learning. Would you say it's speed? Is it numerical stability? Is it robustness of the models? I mean, what about explainability, transparency? Those. So are there certain pros and cons you can quickly touch on, Luis?
Great question. Yes. Yeah, normally when people think of quantum computers, they think of speed, but there's other things. We have strong beliefs and some and evidence that they search in better distributions. Like, if I want to model a distribution, sometimes a classical computer has a hard time not just sample it from distribution, but actually like finding the correct distribution. Whereas quantum computers have shown improvement in being able to model the distribution. So not speed, but actual performance. So when we look at quantum supremacy, we look at everything. We look at all these aspects.
Great. So thank you for that, Luis. I know there's other questions too, but I want to be respectful of everybody's time. So I think with this, we'll close our session for the day. And you've given your links, Luis, on YouTube, your Twitter, and very much appreciate the 40% off on the book. That's always a very good thing to have. But I just want to point out, Luis, it's always good to talk to you. And that's the reason why you are a public intellectual and a science communicator par excellence. I would advise everybody to go check out your videos with Udacity. Also check out your videos on your website, and you've started doing reinforcement learning videos, which is very exciting.
Yeah.
So looking forward to, as you populate, after the book finishes up, after you populate your YouTube channel more regularly. That's a big shout out to you, Luis. Thank you.
Thank you so much, Vic. Thanks for the invitation. I really enjoyed it. It's a great crowd, great questions and great answers. That they great insights. So I've had a great time, and so thanks again.
Thanks, Luis, and we'd love to have you back. The conversation is just getting started.
Anytime you want.
Covered the overview, and once the pandemic is over, we'd have to do one of these sessions in person, which is how we got started with Synthetic Intelligence Forum years ago. Was we used to all get together in the basement of the graduate room in Harvard and Spadina and U of T. So we'll have to maybe come out to you by Waterloo or do it in Toronto or Ottawa.
Welcome to Toronto. Absolutely.
Yes, with pleasure. Thank you, Luis. Thanks everybody, and we'll see you again very soon.
Thank you.
For now.
Have a great day. Thank you. Bye.